Thank you. So, we are nearly at the end of the workshop. So when I got the first workshop notice, I opened the email and was very surprised to see the title. Okay? The title says, as you can see, the entering a golden age of galaxy cluster studies. And that made me realize that, oh, this is the golden age of cluster studies. So somehow the organizing committee of this workshop named, right? Is that right? Yeah. You agreed that we are really entering this golden age. And after I read the title, I started to think that there was similar moment in the past. So I'd like to briefly mention that moment and want to compare that time with this time. So it's usually, people usually address this work by Meshe as the beginning of cluster finding or observation. And therefore, when there was an AAA meeting in year 2000, Andrea Bibiano made a review. He reviewed cluster science for 200 years, from 1784 to 1983. Okay? So that's exactly 200 years, but he chose to review up to only 1983, not only because of that, but also because there are too many papers after that. So he said that it would be very difficult to review the cluster science papers after that period. And in 1980s, so I think the previous golden age of cluster science was the second half of 1980s and 1990s. There are several reasons for this golden age at the time. Okay, this is my opinion. So I just thought of this, I saw the title this time. So in 1980s, I can list a few major events. So the first one was, there was the first large galaxy redshift survey of galaxies revealed in the three-dimensional large structures with cluster located in cosmic web knots. And therefore, the supercluster was confirmed, cosmic void was found, well, not all in 1980s, but around that time. The filaments and worlds are recognized, and the 3D clustering measured. And there was also the milestone paper by Alan Dressler showing the galaxy, cluster galaxy morphology in clusters. And also the luminosity of chemical segregation and star formation H1 gas efficiency segregation also well established by the time. And there was also extensive X-ray survey of Abel clusters performed by then. And at the same time, I also want to emphasize that large cosmological embodied simulations start to become popular. Okay? Before 1980s, there were only tiny simulations by a few people with very efficient code. But in the 80s, there are several groups in the world who was making, at that time, reasonably very large simulations, which can show the formation and evolution of clusters in embodied simulations. So I thought there was a previous golden age in cluster science. And now, the committee called this time as the another golden age of galaxy cluster science. And I think that's mostly driven by new observations. So I think there's some difference between this golden age and the previous golden age in 1980s. And as you all know, there are many equipment which can carry out excellent observations in massive way now built, and they are ongoing. and also on ground and space and high-tech knowledge is also available. There are many projects like using Subaru and projects like SPT and also X-ray and so on. Okay? And also there are wide survey scale observations and deep targeted observations in multi-band and multi-probe observations. Okay, so all these observations produces catalogs, very useful statistical samples, and these catalogs can be used to give us physical quantities. And they can be used to estimate the cluster mass. I mean, there are many cluster mass tracers like London's and CMB, synapse LWC effect, and X-ray, and kinematics, and with lensing. And we also begin to have many data that can be potentially useful to identify high-redshift galaxies, high-redshift clusters and protoclusters. And we can also study gas properties, ice shell properties, and also the properties of individual member galaxies. And we can also study the clustering of clusters as a function of redshift. And in order to convert raw material in the catalog to these physical quantities, we need a lot of theory. And theory and also the scaling relations and also the very accurate knowledge on the systematics. And they can include theory behind the mass calculation and gravitational lensing physics, and also many nonlinear corrections, either analytical or numerical. And all this requires a lot of theory and simulation. And therefore, I'd like to emphasize that in parallel with this development of observation, there should be an extensive study and also development in the field of simulation as well. So I put simulation at the same importance level with observation as a theorist. To perform these simulations, we need to have theory and also the simulation code. And each simulation is simulating a particular cosmological models. And to start cosmological models, you have to have this governing equation, the set of governing equations. And there are many kinds of new cosmological models. And for each models, they have to have different governing equations. And that depends on many things, including, not only including the shape of power spectrum, or shape and amplitude of power spectrum, but also depending on dark matter physics and dark energy physics, and also the geometry of the universe. The simulation, the universe evolves in different ways, and they have direct impact on structure formation. In addition to these cosmological theories, we also need more uncertain astrophysics of star formation and feedback, and that is constantly being developed, but we still have a lot far away to go more. And even if we have a full set of theories, the simulation would be impossible if we don't have good code, efficient code, and also the good computing facility. And now, embodied simulation is not very useful in the study of galaxy formation and cluster science. So one has to go to hydro simulation at least. And in addition to hydrodynamics, we may have to also include radiation and magnetic field in the future. Maybe some code already do this. And there is also a lot of debate between the Lagrange code and Eulerian code or hybrid code, and you have to choose and make a detailed comparison in order to understand all kind of artifacts in the simulation. And particularly in the cluster science, even the restriction in the computing resource, zoom-in simulation is unavoidable. So we have to have at least 1 gigaparsec box size, and we have to have the resolution much better than 1 per kiloparsec. And it's impossible to simulate the whole box. So zoom-in simulation is kind of mandatory. And even in zoom-in simulations, the parallelism, particularly the 3-dimensional parallelism, is necessary, combining MPI, OpenMP, and GPU computing. So once you are ready to make the simulations, and if you are lucky, you have a large bunch of time and run these simulations for a few years, and you will get some simulation data. And then you put the input from observation and reflect all the observational effects, such as the Paxson threshold or selection function and all kind of those things, to make mock samples. And using these mock samples, you can derive many theoretical predictions or the estimate of the important systematics. And you, for example, you can do for the modeling of abundance and lengthening signal and X-ray properties, and you can improve the mass function formula for each cosmological models to very high accuracy. And now, after you adopt hydrodynamics, you can now understand the baryon impact in the simulation, and also the impact of cluster identification method can be measured in these mock samples. And there are also, these mock samples are useful to estimate the bias that in, for example, the mass estimation that adopts some assumptions like hydrostatic equilibrium or dynamic equilibrium. And using those things, we can calibrate the scaling relation. So the findings over there will go there, and to help people to convert this catalog to physical quantities. So once we are ready to use both observational data and simulation data, then we can do many sciences. There will be many more, but I just name a few of them. And for example, the cluster cosmology is one of the most, maybe to myself, the most important topic of mine. And cluster formation and the state of cluster is also a very interesting topic to work on, and galaxy properties and their evolution in this cluster environment in comparison to field is also very interesting. There are other infinitely many interesting topics. And using in the case of cluster cosmology, the main motivation for the start of the cluster cosmology is the realization that this massive end of mass function is very sensitive to cosmology. Because in 1980s, we didn't know omega matter. So the standard model was omega matter equal 1, Einstein de Sitter model. And there are many observers claiming that omega matter doesn't seem to be 1, and it seems to be 0.1 or 0.3, like that. And then people realized that the number of these massive objects that is periodized on the galaxy cluster scale, because galaxy clusters are the objects that are just forming around between redshift 1 and now, they will be very sensitive to this cosmology. Okay? Because if you change omega matter, the shape of power spectrum changes, and this mass function will be very different between these two models. So that was the motivation. But it turned out that the problem was not so easy. So as I briefly showed during the discussion session, I told you that now the other competing cosmological probes, they are reaching to the accuracy. Like, they can distinguish between W equal -1 and W equal -0.9 Lagrange model at better than 3 sigma. Okay? So to be computed for the cluster cosmology using cluster mass function or cluster count, the kind of accuracy in the cluster count has to be better than 1% accuracy. Okay? So you can measure some point over here, or you can compare this point with some point at higher redshift and so on. But the accuracy has to be of order of 1%. So that's quite a challenging task. But still, that's the main topic of this community. The second one is cluster formation and state. And now we begin to have very large samples of 3D-dimensional samples, both in photometry and spectroscopy. And they can give us the opportunity to study the internal structure of clusters with good membership, with high purity and completeness, and also the protoclusters can be studied at higher and higher redshift. In particular, protocluster science is getting mature compared to more than 5 years ago. And intercluster medium and intercluster light science is also becoming one of the main topics in this field. And again, to do this science, particularly I want to point out the importance of having statistical sample to identify protocluster from here. So I said that in my case, I want to identify protoclusters as the region that will collapse at before G equals 0. Okay? So in order to do that, I have to have an estimation of total mass within certain radius, and if that overdensity within that radius is above the critical density of the spherical collapse by G equals 0, then I know this is going to be a cluster. Okay? If the mass is above 10 to the 14 solar mass. But in order to apply this criteria to search for protocluster, the sample has to be much larger than 20 megaparsec. So typically 100 megaparsec or larger. So we need that kind of sample in the future with good spectroscopic redshift. Galaxy properties and evolution. Of course, this is a very interesting topic also to myself, and I expected to have unbiased sample of member galaxies and deep observational samples out to large volume, and at the same time to understand the physics of these member galaxies, we need to have the simulations reaching both bare sample and also the mass resolution in the initial condition and the force resolution during evolution with working at least. We cannot use, and also because we don't know, we cannot apply the correct mechanism, but with working star formation and feedback mechanism. And through this, we hope to understand the environmental dependence of various astrophysical processes in galaxies in different environments. For example, we want to understand the emergence of galaxy cluster connections. There are many aspects of galaxy cluster connections. We want to understand when they first appear and what's the mechanism for these connections. And we want to also understand the gas physics, gas dynamics, and so on, and also morphology evolution too. But unfortunately, the development of the simulation is very slow. So for example, on the left, I'm showing the number density of galaxies found in simulations as a function of redshift in few famous simulations. And the dots are the galaxies found in JWST observation, mostly. And you see that the simulation basically do not predict any massive galaxies. These are the galaxies above about 10 to the 9.4 or above about that threshold. So they are, well, at that time they are massive ones. Okay? But even so, these simulations are not able to produce that. Even our simulation, HR5, the green line, okay, so that is a bit larger than Eagle simulation, but still we don't expect this value. And we also got the JWS data and actually measured the number density of these JWS galaxies with mass above 10 to the 9 solar mass, and there is a lot more than HR5 predictions. But recently, the people who ran Sept code, they made a new simulation. The Sept code is one of the SPH code, and they claim that they are able to fit this observation, okay, using their simulations. So their simulation is pretty big, but there is something strange. So there are two lines, and one line is the result from bigger box, okay, 400 Comoving megaparsec box with 1.4 proper kiloparsec resolution. And the bottom one, this line, is the 2 times smaller box and 2 times higher resolution. And the one that fits with observational data is this higher resolution small box simulations. So depending on the box size, one data matches and the other one doesn't match it. So as I said, there's no convergence in the hydro simulations yet. So community, the simulation community is trying to improve our subgrid physics to explain whatever the new observation comes. We can also think of many other sciences. One of the science I can think of is the cosmic void. Because cosmic void is just the flipped version of a cosmic cluster in the initial condition. The starting void, applying the definition equivalent to the definition for galaxy cluster may be important. And therefore, the cosmic void and studying the proto void will be also important. And also the connection between clusters and superclusters and other large structure is also a very interesting topic to study. Okay, so I could not review the talks given by individual people because there are so many talks. So I just put all the talks into one previous slide. So that's one page summary of this workshop. But I cannot go on without talking about the workshop held in 2019, okay? Because I think this workshop is quite keenly related with this previous one. And here is this one. So before I came here, I thought that it may be interesting to compare the talks given at 2019 workshop and 2025 workshop. Okay, so but that was too much work. There were too many talks, and so what I did was for the first time in my life, I asked ChatGPT to do this. And then ChatGPT found 10 people that are common in these two workshops, and these are the people. Okay, so it did a very nice comparison and also the analysis of the talks. given by the same people. For example, the Inwon Chu, he talked about this constraining richness to mass relation in 2019, but then this time he talked about cosmological application of clusters. And the machine said that he evolved from method to cosmology. Is that right? And also you can look at the things. Well, Tadayuki said the same thing. So there was some, of course, but they are not exactly some. There's a lot of more. At least I heard that the ultimate was funded. Okay? So there's some development. Okay. So after that, I found that I can ask 3 or 4 questions per day. So after a few questions, ChatGPT just said, stop, ask me 1 day later. Okay, so before it refuses, I asked 1 more question to make this plot. Okay, so the x-axis is the type of research, okay, so observational and simulation theory, and mixed one, and also instrumentation. So, and the y-axis is the topics, science topics. Okay? And it's not clear. I mean, if I combine mixed one and simulation, there may be a comparable, but still, one big trend of the talks given in this workshop was that there were a lot of observation talks. Okay? So that was one thing. And in comparison, the simulation and theory talks was relatively fewer. Okay? And there was another one was that there's relatively bigger emphasis on cluster mass and cluster cosmology using cluster mass. Okay? So that was one thing. But I think the only very clear message is that simulation was weaker compared to observation. So the ChatGPT not only just compared these two, but it was much more intelligent I expected, and it also gave me the overall trend and messages by comparing these two, the talks in 2 workshops. And I read through this, and I found this quite gives us some very nice messages. Okay? So we can agree that the people are moving from the method and pilot studies to actually large and multi-wavelength surveys and spectroscopy. And people are now going to precision mass calibration and using multi-probe modeling and so on. And now I certainly agree that the protoclusters, the field of protoclusters became mature, and there are a lot more talks on protoclusters. But one thing I am not still happy with was the definition of protoclusters doesn't seem to be converging yet. Okay? So I think I mentioned that in 2019. So when I listened to people's talk in 2019, when people talk about protoclusters, everybody uses their own definitions for the detection of the protoclusters. So the one protocluster by one speaker could not compare with the second speakers. So just couldn't understand the implication of these studies. And there may be, the situation has not changed too much, yeah? And also, we noticed that the ICL and low surface planet science, and then people are also using U-tracers to study dark matter properties. And the pre-processing and environmental effect, there's a lot of works there too. And there are new instruments and facilities are coming. Okay? That's also exciting news. Personally, I like the development in dark matter and fundamental physics probes, and they seem to be such topics in this topic seems to be more diverse and robust. So that was also very good. Unfortunately, I didn't listen too much about making simulations. So maybe next time I hope to have more presentations in this method and topics. Okay, so the conclusion of this summary, I think the first conclusion is this workshop is a great success. So that's the conclusion. Okay? But if I have to say why, there are many things we have learned. I personally learned a lot during the past 4 days, and this is a summary of previous 2 pages. So many moved from method to pilot studies to large-scale multi-survey implementations and precision analysis. And also the key science driven in this year includes the precision mass calibration and proto-clusters at very high redshift, and ICL as tracer and constraint on dark matter, and full sky statistical reconstruction enabling discovery and cosmology. And there are also many instrumental and survey advances are the main cause for this acceleration between this period. And that is why we feel that we are in the beginning of golden age, of new golden age of cluster science. But in addition to this conclusion, I'd like to make some proposal, and I have 2. And one is that I wish the organizers of this meeting to initiate maybe small working group, okay, for leading focused discussion on proto-cluster definition and standard identification method. So that will be, if there is any conclusion from this working group, there will be a very helpful contribution to the community. The second one is in the next workshop. I'm not sure if it's going to happen next year or 2 years later, but in the next time, I wish there is a little more, relatively a little more theory and simulation talks. So that's the recommendation I'd like to make. So I want to say, I'd like to say 공식, okay, and 축하합니다, and 오메데토 고자이마스 for having the first East Asian workshop on galaxy clusters. Okay, thank you, and see you again in either Korea or Japan next time. Thank you.
Very useful summary as usual. So usually we don't take questions.
There is no question to summary talks.
If anyone wants to say something? No? Okay, let's thank Sang again.